going to discuss whether we can prove that the CMB anisotropies are of quantum mechanical origin. And to discuss this question, I have organized the talk in the following way. So in the first part, and this will be quite brief, I'm going to introduce the subject and mainly give my motivations. Then I will discuss the theory of cosmological perturbation of quantum mechanical origin, since this is the main tool that we are going to use for our discussion. And then in the third part, I will discuss whether the perturbations can be seen as a real quantum system, or if at the effective level they can be described in classical terms. And I will use the result of this discussion in the fourth part to discuss whether we can extract a direct or observe a direct signature of the quantumness of the perturbations. And at the end, I will very briefly recap and give my conclusions. So let's start with the motivations. So we know that according to inflation, the perturbations that we observe in our universe originate from quantum fluctuations of the gravitational field and of the scalar field, typically the inflaton field, the field responsible for inflation. These fluctuations are then amplified by gravitational instability and stretch to very large distances, to cosmological distances, by cosmic expansion. So this is a very strong statement, because if true, it means that all the structures that we see, that we observe in our universe, such as CMB anisotropies, but also galaxy, clusters of galaxy, and so on, are nothing but quantum fluctuations. So, of course, we have already some indirect evidence for this statement, and the indirect evidence for this statement is simply the fact that if we postulate this mechanism, it seems that what can be inferred from this assumption fits very well the data. So typically, if we assume quantum fluctuation in the very early universe and derive the consequences, we find typically a power spectrum which seems to be in a very good agreement with the most recent data, typically the Planck data that have probed the CMB anisotropy and measured the power spectrum with exquisite accuracy. So this gives, as I was saying, an indirect confirmation of the quantum mechanical nature of those perturbations. But here, I would like to discuss something which is related, which is not equivalent to what I have said. Namely, I would like to investigate whether we can find a direct signature in the sky of these quantum fluctuations. So is there something, an observations or a pattern that we can observe in the sky and that can be understood only if we use quantum mechanics? Is there such a signature? Is this possible to really take concretely, let's say, the Planck data, the Planck map of the CMB anisotropies, and is it possible to extract from this map a direct signature of the nature of the perturbations? So this is the main line of thought that I will be following during this talk. So in order to discuss this question, obviously, I need to spend some time on the theory of cosmological perturbation, and this is what I'm going to do in the next few slides. So here I just repeat what I have said. The fluctuations are quantum in nature. They are amplified and then stretched to cosmic expansion. So technically, how do we deal with this perturbation? Well, we just expand the gravitational field, that is to say the metric tensor and the scalar field, let's assume here that there is only one scalar field, the inflaton field, the field for responsible for inflation. So I'm considering vanilla models of inflation, but considering more complicated model would not change the discussion. And we expand them around an expanding space-time which is homogeneous and isotropic. So this is why the metric tensor only depends on time here, and the background scalar field only depends on time as well, plus small fluctuations. And we will work at first order during this talk, which are inhomogeneous, so they depend on space, and they are quantum. So I put a hat on delta G mu nu and on delta phi. And these fluctuations are the fluctuation that we are going to discuss. So if you want simple analogy, it's a bit like in a crystal. We have a classical lattice, which would be the equivalent of our expanding space-time. And on top of this lattice, we consider quantum excitations, the phonons. So in some sense, here we consider the gravitational phonons on top of a Friedmann-Lemaitre-Robertson-Walker expanding homogeneous and isotropic space-time. And for those of you who are familiar with cosmological perturbations, there are three types of perturbations: scalar, vector, and tensor. And here in this talk, I will mainly concentrate on scalar perturbations because they are the most important ones, since they give they are responsible for the main contribution in the CMB. And in addition, I could reproduce the same discussion for tensor. This will not change anything to what I'm going to say. So I will just focus on scalar perturbations. And well, in that case, and in the case of single field inflation, it's well known that you can describe the scalar fluctuation, so the small ripples, inhomogeneous ripples on top of this expanding background, with a single quantity that I have denoted here, zeta, which is curvature perturbation, which is like a scalar quantity living on top of this expanding space-time, which is in this framework, of course, a quantum operator. So it represents the small fluctuations that we have at the beginning of inflation, and that you can expand as usual in terms of creation and annihilation operator. The only thing that I would like to notice here is that you see that the creation and annihilation operator are a function of time. So if we were considering a field on top of Minkowski spacetime, as in ordinary QFT, of course, the time dependence of those operators would be something like exponential I omega t. But here, of course, curvature perturbation live on top of a Friedmann-Lemaitre-Robertson-Walker spacetime. So the time dependence of those operators is more complicated, as we are going to see. But apart from this difference, this quantity zeta describes absolutely everything we need to know about scalar perturbations. And in addition, it's directly related to the observations because it's directly related to temperature fluctuation on large scales. So as I was saying, this is a quantity which depends on time, and the time dependence of this quantity is controlled by the Hamiltonian of the theory. And the Hamiltonian of the theory is going by this expression that you can see on the slide. So before discussing and explaining this Hamiltonian very quickly, I want just to point out that really this Hamiltonian, it derives from first principle, in the sense that to obtain it, you take the action of gravity, Einstein-Hilbert action, plus the action of a scalar field. You expand everything up to second order, because you want first order equation of motion. You substitute the expansion that I have shown before, and you end up with this Hamiltonian. So it's really, there is no extra assumption. It really comes from GR plus a scalar field, if you wish. And you see that this Hamiltonian, it's made of two pieces. There is the first piece, and here you recognize the Hamiltonian of a free field. A field is an infinite collection of harmonic oscillators. So you recognize with the integral over d3k the sum over the Hamiltonian of each Fourier mode. And there is a second term, which is more interesting for what we want to discuss here, which is this one, and which is, in some sense, responsible for the interaction between those quantum fluctuations and the classical background. So you see, this term is itself, it's made of two pieces. There is first this term in front of it. So this term is like a time-dependent coupling constant. So A here is the Friedmann-Lemaitre-Robertson-Walker scale factor, so the function that tells you how the universe expands. And epsilon 1 is the first floral parameter. So in fact, it's just a given expression of the scale. It's given in terms of the scale factor and its derivative. The details are not important at this moment. The only thing we need to know is that this time-dependent coupling constant only depends on the scale factor and on its derivative. And if you take the derivative, yes.
Can I interrupt you to just ask a couple of questions here quickly?
Sure.
So one of the questions is that, so here gravity is still classical. There's no gravity. This is a classical gravity and the quantum scalar field.
Not really. No. It's I mean, let me go. No. Yes. You see, so I have put a hat on delta G mu nu, so you have a classical background. So it's true that at the level of the background, gravity is classical, but the quantum fluctuation of the metric tensor, I'm sorry, the fluctuation of the metric tensor are quantized. So in this sense, there is some quantum gravity in this problem. Of course, at a very modest level, we are at linear level. So this explains, I'm sorry, yes.
Right. So, but you use the operator CK to quantize both the scalar field and the gravitational, both the gravitational fluctuation and the scalar fluctuation. Is that?
In fact, you can show that everything can be expressed in terms of this variable zeta, which is a combination of delta G mu nu and delta phi, if you wish.
I see. Okay, thank you. Now it's much clearer. Okay. And the time is some kind of cosmological time?
Yes, the time is cosmic time, standard cosmic time.
Okay.
Yes. So I was saying that this POM field, as we would say in quantum optics, so this time-dependent coupling constant depends only on the scale factor and its derivative. And if you take the scale factor to be a constant, namely Minkowski spacetime, ordinary QFT, then this coupling constant vanishes. So it's really the fact that the universe is expanding that makes this term non-vanishing. And the other part of the second term is also interesting. And in particular, you see the structure K minus K. Well, it just means that you create particles, pair of particles with opposite momenta, K minus K. So maybe I can offer another analogy for this inflationary mechanism for the productions of perturbations. Maybe it looks a bit speculative. After all, we are talking about the early universe. The energy scales of inflation can be as high as 10 to the 15 GeV. Maybe it sounds like very speculative physics, but actually, I think this mechanism for the creations of the perturbation is in fact quite conservative, because it belongs to a class of effects with which we are very familiar in quantum field theory. In particular, this is a mechanism which is very similar to the Schwinger effect. So I remind you that the Schwinger effect is the following. You take a fermion, so for instance, a quantum field associated with electron and positron, and you consider a situation where this field, this quantum field, interact with a classical source, which is, in that case, a classical electric field. And Schwinger in the 50s uh, uh, showed that this causes the productions of particles. You extract pairs of electrons and positrons from the vacuum due to the interaction of this quantum field with the classical electric field. And Schwinger computed the number of particles that you can extract as a function of the strength of the source, which is in that case the magnitude of the electric field. And this is a very interesting effect because this is one of the few effects in quantum field theory which can be calculated exactly. And the mechanism for the inflationary cosmological perturbation is exactly the same thing. What plays the role of the electron and positron field are the quantum perturbations. So if you wish, the inhomogeneities in the gravitational and scalar fields. The source, the classical source, is just the background gravitational field, is the scale factor. And when you calculate correlation functions, for instance, the power spectrum, well, you find that it's controlled by the strength of the source, which is in that case the Hubble parameter. So there is a direct analogy between the Schwinger effect and the mechanism for producing perturbation during inflation. And in fact, this type of effect, they belong to even a larger class of effect because it's also similar to the dynamical Schwinger effect, to the dynamical Casimir effect that has been seen in the lab and so on. So even if it sounds a bit speculative at first sight, I think the physics on which it rests is quite robust and conservative. Uh, this being said, now let's discuss the initial conditions. So this is a plot that probably many of you have already seen. So on the vertical axis, I have put the physical wavelengths that are relevant for our problem. And on the horizontal axis, I have put time, the logarithm of the scale factor, so the number of e-folds. And the colored lines are the evolution of the Hubble radius. So the Hubble radius being defined as the inverse of the Hubble parameter. So you see it's constant during inflation, and then during the subsequently during radiation or matter-dominated era, it grows. And the black line here represents the physical wavelength of a Fourier mode of astrophysical interest today. And the interesting point, and one of the main success and main reasons why people are so attracted by the theory of inflation, is that initially the wavelength of the perturbation is smaller than the Hubble radius. So what does that mean? It means that initially, at the very beginning of inflation, the Fourier mode does not fill the expansion of space-time. I'm sorry. Okay. So it does not fill the expansion of space-time, and therefore you can postulate. I mean, you have well justified and well motivated initial condition. You start from the vacuum state, which is well defined in that case, and this is called the adiabatic vacuum or the Bunch-Davies vacuum state. And this is nothing but the ordinary vacuum state of standard quantum field theory. And this is one of the great advantage of inflation, is that it gives you a preferred choice for the initial conditions for the perturbations. And so let's discuss a little bit more this initial state. So if I write the quantum state of the perturbation in terms of a functional. So I can always see the functional of the curvature perturbation. I can always write it at least at linear order. I can always write it as a product of wave function for each mode. So I can always write it as a product of psi of zeta k, zeta minus k, k wave number of the created pairs of particles. And in fact, the initial state, that the Bunch-Davies vacuum state, in that case, is nothing but the ground state of an harmonic oscillator. As you can see here, you just recognize the Gaussian, which is nothing but the ground state of the harmonic oscillator. And usually we call it a two-mode vacuum coherent state. So this is, well, in quantum optics, people would say that this is the most classical state we can imagine. A classical light, for instance, is described in terms of a coherent state. So this is the initial state. But as we have seen, this is the state of the perturbation where their wavelengths are inside the Hubble radius, but as the universe is expanding, there was a question or no? Okay, no, I thought there was a question. Sorry, I heard something. Okay, so initially, when the wavelength of the perturbation is smaller than the Hubble radius, um, we have this Gaussian state. But as the universe expands, the mode crosses out the Hubble radius and becomes larger than the Hubble radius, and the state is going to evolve in time. And the state is going to evolve into a two-mode vacuum squeezed state, which I have represented here. So it's no longer a circle here, it's now an ellipse, and the wave function is given by this expression. So you see that this is still a Gaussian state, but there is a new parameter R here, which is responsible for the appearance of this ellipse, and this ellipse which represents some correlation between k and minus k. And in fact, this parameter R is growing with time and is in fact directly the so-called squeezing parameter, which is well known in quantum optics. So from the initial vacuum coherent state, due to the expansion of space-time, our quantum fluctuation evolves into a two-mode vacuum squeezed state. The squeezing being determined by the way the universe expands during inflation and then subsequently. So what's the value of the squeezing parameter? Here, there is also an interesting analogy. First of all, let's just consider the CMB itself. You know that the CMB has a black body shape, a temperature of 2.7 Kelvin. Here I have represented the black body spectrum. It's the green line on the left of the screen. And the red points, the red dots, are the measurement. In fact, the error bars have been magnified by a factor of 400, because otherwise they would be smaller than the thickness of the green line. So you see that we have a very accurate black body, and in fact, it's probably the most accurate black body ever produced in nature, because in the lab we are not able to produce such a perfect black body. And in some sense, there is an analogy for the perturbations, in the sense that I believe, at least to my knowledge, the CMB anisotropy are placed in the strongest squeezed state ever produced in nature, because the value of the squeezing parameter, which describe the flatness of the ellipse that I have shown before, is of the order of 100, let's say, while people in the lab are fighting to achieve a value of R, a few, or typically something like that. So really, the message here is that not only we have a too much squeezed state, but it's very strongly squeezed. Okay, so this is the context in which we are now going to address the main question. So are these perturbations quantum or effectively classical? So at first sight, of course, they are quantum uh, because all the description that I have used so far is quantum. But what I really want to know is that whether they can be described by classical equation in the very same way, to offer a very simple analogy that if you uh, calculate the trajectory of a satellite around the Earth. Of course, the satellite is a quantum object because it's made of atoms, and atoms are described by quantum mechanics, but nobody would use quantum mechanics to calculate the trajectory of the satellite, and in that case, we know that effectively the satellite is a classical object. So the question that I want to ask is exactly that question. Even if the underlying description of the perturbation is quantum, can we describe them at the classical level? And knowing that, of course, people who are doing the data analysis of the CMB anisotropies, or the Planck or the WMAP people, they never use quantum mechanics to deal with the data. So the funny thing or the interesting point at this stage is that at least at first sight that you can find arguments in favor of the two possibilities. You can find strong argument for the quantumness of the perturbations, and at the same time you can find arguments in favor of a description in classical terms. So let's try to discuss those arguments. So I will not go through all these arguments due to lack of time, but I'm going to discuss some of them. So let's start with the arguments about the quantumness of the perturbations. So the first one is that a two-mode squeezed state is an entangled state. And here I show again the slide on which displays the wave function of the perturbation. So the two-mode vacuum squeezed state here at the bottom of the slide. And in fact, it's very easy to see that you cannot factorize this state and you cannot write it as a product of a wave function for zeta k and zeta minus k, which means that this vacuum squeezed state is an entangled state. And I think that everybody would agree that entanglement is the prototype of a quantum property. And moreover, you can even show that if you send the squeezing parameter R to infinity, a two-mode vacuum squeezed state goes to an EPR state, the state used by Einstein, Podolsky, and Rosen to discuss the weird property of quantum mechanics. So probably the state in which the perturbations are placed is the most accurate representation of an EPR state ever found in nature. And so facing this, I think that anyone would conclude that a classical description of the perturbation is not possible because entanglement we don't see, or EPR we don't see how we could describe it classically. On the contrary, this is, as I repeat, this is used in order to discuss and show, exhibit the weird properties of quantum mechanics. Another argument is that the quantum discord is large. So what is quantum discord? Quantum discord is a tool that is used in quantum information. So probably you know more about it than I do, but very briefly, it's the idea is it's a kind of criterion to decide whether a system is classical or quantum. So what you do, you cut your system into two subsystems such that you deal with a bipartite system, and you calculate the correlations between these two subsystems, and you study whether these correlations are quantum or classical. And so the quantum discord corresponds to two different ways to calculate the mutual information between the two systems. These two information coincide classically. So the difference between the two, which is the discord, is zero. But in quantum mechanics, this is not necessarily the case. And therefore, a non-vanishing quantum discord signals that there is something quantum in the system, if you wish. So we have computed the quantum discord for the two-mode squeeze state, and the plot that you see on the slide is a representation of that result. So on the vertical axis, you have the quantum discord. So you see in that case, it's a bipartite system. One subsystem is mode K, the other subsystem is mode minus K. So this is the discord between these two systems as a function on the horizontal axis of the squeezing parameter R. So you see that initially the discord, when R is zero, the discord is zero. And this is consistent with the fact that initially we have a coherent state. And the coherent state, again, in some sense, the most classical state that you can imagine. It's the state, again, that is used to describe classical light. So it makes sense that the discord is zero in that case. But as R is increasing, then the discord becomes non-vanishing. And for quite large values of R, it grows linearly with the squeezing parameter. So this means that in our case, the discord is very large and we deal with a very discordant quantum state. And therefore, this is another argument in favor of perturbation that cannot be described in classical terms. So now, in some sense, it seems that the answer is pretty clear. If I want to describe, it seems that if I ask whether I can describe the perturbation classically, it seems that the answer is a simple no, I can't. But it's not that simple. And now let me go through the arguments that have been used by people to argue that despite what I have explained, you can describe the perturbation classically. And the first reason is that because the Wigner function of the squeezed state is positive definite, a stochastic description is available. So let me explain now in some details what this sentence really means. So people argue that a stochastic description is available, is valid, if the quantum and the stochastic correlation function always coincide. So in some sense, if you want to characterize the patterns of the CMB, usually calculate the correlation function, but if each time you calculate a quantum correlation function, if each time you can reproduce this result with a stochastic calculation, then you argue that some quantum to classical transition has happened in the system. So what does it mean exactly technically? Well, let's consider phase space. So here I consider a four-dimensional phase space. So I have two coordinates, two position coordinates in some sense, q of k and q of minus k for the mode k and minus k, and the two momenta associated, pi of k and pi of minus k. So this means a four-dimensional phase space. And I consider a function a, which lives in this phase space. And I would say that a stochastic description is possible if any quantum mean value can be reproduced in terms of a stochastic mean value. And by stochastic mean value, I mean this standard equation, namely I calculate the stochastic mean value of the function a by integrating the function a over space, over phase space with a probability density function W that we need to discuss. So if each time I calculate a quantum average, I can reproduce it with a stochastic average, I say that the system is classical. And in fact, I need more. Of course, in order for this calculation to be meaningful, I need the probability density function to be positive everywhere, and I need it to obey the classical equation of motion. So I have three rules for an equivalence between a quantum and a stochastic picture, if you wish. And now we are going to study under which condition are these three rules satisfied. So let's start by the first rule. And in order to discuss the first rule, it's interesting to introduce the Weil transform of an operator. So what is the Weil transform of an operator? You take an operator and it gives you, it returns a function in phase space. So you take an operator at, and you take its Weil transform, TW of A, and it gives a function in phase space, which is given by this, which is basically the Fourier transform of its matrix element in position space. This is the definition of the Fourier of the Weil transform, and concretely you can calculate the Weil transform of any operator. So for instance, if you take any power of one of these components, so this means any power of position or momentum, you find that the Weil transform of the operator is exactly the corresponding classical function. But if you, on the other hand, if you calculate the Weil transform of a product of two operators, Q or pi, you find that it's not always the corresponding classical function, especially if you take Q and pi, and we understand why. It's simply because Q and pi do not commute. And this is the reason why you don't find a coincidence between those two quantities. Now, the Weil transform has a very important property, which is always valid, which is that the trace of the product of two operators, A and B, is the integral over phase space of their Weil product. So this immediately tells you that the mean value, the quantum mean value of the operator A, which is the trace of A times the density matrix of the system, is the stochastic expectation value of its Weil transform if the probability density function I was mentioning before is taken to be the Weil transform of the density matrix. And the Weil transform of the density matrix is the Wigner function of the system. So this means that this equation is always true if I take for the probability density function the Wigner function, and if for the operator A, its Weil transform equals the corresponding classical function. Then stochastic averages and quantum averages always coincide. Of course, it is not obvious that the Weil transform of the operator will always be equal to the corresponding classical function. But if this is true, then we always have this property. In particular, this is true for any power of curvature perturbation. So this means that this will be true for the power spectrum, this will be true for the bispectrum, this will be true for the trispectrum, and so on. So this is for the first rule. Now, what about the positivity of the Wigner function? So the positivity of the Wigner function, it's not always true, but it's true for cosmological perturbations. It's not always true. So why? Because we have seen that the Wigner function is the Weil transform of the density matrix. A squeezed state is a Gaussian state. The Fourier transform of a Gaussian state is a Gaussian. And therefore, the Wigner function is a Gaussian as well, and is positive definite. So this property is true for cosmological perturbations. And we see here, in some sense, the association between classical property and positivity of the Wigner function, which is a standard thing in quantum mechanics. I believe it comes from the calculation of the Wigner function for a Schrödinger cat. This is what I have reproduced on the left part of the slide. You take a Schrödinger cat, so the superposition of a wave packet at the plus position plus a wave packet at the minus position. If you calculate the Wigner function of this state, as you can see, you obtain two bumps, which would be the Wigner function of the two wave packet. But in between, you have those oscillations, which are, of course, nothing but the interference between the two. And you see that because of this interference, the Wigner function can be negative. This is why people sometimes use the positivity of the Wigner function as a criterion for classicality. Anyway, in our case, in the case of cosmological perturbation, the Wigner function is positive. And finally, W obeys classical equation of motion. In fact, this is always true for any quadratic Hamiltonian. And our Hamiltonian is quadratic, therefore, this is true for cosmological perturbations. So, what does that mean? This means that it seems that at least for all the quantities that we have managed so far to measure and observe, such as the power spectrum, the bispectrum, the non-Gaussianities, it seems that a classical description is indeed available. We don't need quantum mechanics to calculate those correlation functions. And please notice that this has nothing to do with the amount of squeezing in the system. So this would not be the case for more complicated quantities, such the one that I have reproduced at the bottom of the slide. But for the quantities that we observe, which are powers of the curvature perturbation, this is always true. There are other arguments in favor of classical description. For instance, WKB. There is a sense in which this two-mode vacuum state is a WKB state. So I just signal this. I have no time to discuss it at this stage. And of course, there is the question of decoherence that I also skip at this stage. So let's now recap where we stand. On one hand, we have a two-mode squeezed state with a positive Wigner function, and which is such that there is absolutely no need of quantum mechanics at all to calculate the correlation function that we are interested in. So the system in this sense can be described in purely classical terms. It seems that a quantum to classical transition has taken place. On the other hand, the system is placed in a vacuum state, which is an entangled state and which is strongly squeezed, so which is almost as an EPR quantum state, which is known to be the prototypical non-classical state. So the question is, how can these two statements be true at the same time? It sounds like a bit as a contradiction or as a paradox. So can we understand this question? And here I would like to make an aside and an historical remark, is that exactly the same situation, in fact, was discussed by John Bell in his famous book, Speakable and Unspeakable in Quantum Mechanics. So for people working in cosmology, there is a chapter in this book which is entitled, I think, Quantum Mechanics for Cosmologists, which is well known, which is cited all the time. But actually, it turns out that the most interesting chapter for cosmologists is not that one, but it's chapter 21, which is entitled EPR correlation and EPW distribution. And John Bell discussed exactly the question that I have described before, not in the context of cosmology, but it's exactly the same question. And you see that the title is EPR correlation. So here he refers to the Bell inequality, which is a way to decide whether a system is quantum or classical, and EPW distribution. EPW stands for Eugene Paul Wigner. This is nothing but the Wigner distribution. So let me describe very quickly what was done by John Bell in that paper, since this is extremely relevant for what we want to discuss. So the main claim of John Bell in this chapter of his book is that if a state has a positive definite Wigner function, then Bell's inequality cannot be violated. So his inequality cannot be violated. So in this sense, John Bell makes the association between classicality and positivity of the Wigner function. And in practice, what he does is that he calculates the Bell operator, you know, the operator which is usually expressed in terms of the spin operator, so which is, if it's less than 2, then the Bell inequality is not violated. If it's larger than 2, then Bell inequality is violated. So here I have reproduced the usual setting for the measurement of the Bell inequalities, such as the one done by Alain Aspect in the 80s. So what Bell does, he calculates the Bell operator for a state with a positive Wigner function and find that there is no Bell inequality violation. And then Bell calculates B again, but for a state, this time with a negative Wigner function. And this time he finds a violation of his inequality. And therefore, he concludes that a positive Wigner function means classicality. So to be totally honest, if you read carefully the chapter, he's quite careful. He says that he's not sure that this has a universal meaning, that is always true, but clearly, at least between the lines, he makes this association. And after his paper, after his publication, Bell's paper has been criticized by a series of other articles, and those other articles have simply argued that the Bell paper is incorrect. So this shows that this question has attracted a lot of attention. And in fact, recently I have written a complete paper on the story of the Bell paper and the criticisms. And so I have confirmed that the paper by Bell that I have just described is incorrect, but it turns out that the paper who have criticized Bell paper are wrong as well. And this is really a fascinating story to follow all this article, the argument and the responses and all that. So everything is described in details in this paper that is on the web, on the internet, on the archive, if you are interested in this story. But this shows that there was some confusion about this question. The confusion, which is very relevant in our case, because it turns out that this is exactly the situation we are in the context of cosmology. And in fact, the situation was clarified only quite recently by Revzen, you see, maybe 10 years or maybe 15 years ago. And the conclusion of Revzen is that it's true that we can say that the system is classical, except for a subset of very specific operators. So let me describe exactly the result obtained by Revzen, or let me give more details about this result. So I believe I still have 10 minutes, maybe, because we started late. Yeah, okay, perfect. Yes, so Revzen has shown that even if the Wigner function is positive definite, there is a class of operators that can lead to non-classical properties. So obviously, these operators are not simple power of curvature perturbation, because we have already seen that for them, classical or stochastic and quantum correlation function coincide. So this is just what I have just said. So this is very interesting for us, because if we could identify those operators and investigate how we can measure them in the CMB, maybe we could, this would be the way to detect a signature of their quantum nature, of the quantum nature of the perturbations. So can I provide an example? Yes, I have a simple example, which is the following. Consider a simple particle moving along a line. one-dimensional problem. Q is its position. So in the context of cosmology, QK would be the position in phase space associated to the mode zeta k of curvature perturbation. But here, let's simplify everything, just a simple particle moving along a line. You define this operator, which resembles, let's say, it's like a sum of projector. It's characterized by the parameter L, you see here, which appears here and in the limit of the integrals. So this operator is like a grading spin operator. So this means that if you take this operator plus its dagger, it gives you Sx, so which is like the x component of a fictitious spin operator. And it's a fictitious spin operator because if you calculate the square of this operator, it gives 1. Now, if you calculate its Weil transform, it's something which is very complicated. It's not at all, it would not be at all equal to the corresponding classical function in phase space. And moreover, you can complete this definition with two other components, S wire and Sz, and show that these three fictitious or pseudo spin operator, they obey SU2 commutation relationship. So they really behave as a spin, if you wish. Then you have spin operators and you calculate the Bell operator and you see whether you have a violation of the Bell inequality. This is what we have done here. So this is here the mean value of the Bell operator versus L. And you see that there are some values of the, so I have forgotten to say that, of course, you calculate the mean value of the Bell operator in a two-mode squeezed state. And you find that for some values of the squeezing parameter, the value of B is larger than 2, signaling a violation of the Bell inequality. Even if this is done with a state, with a quantum state, which has a positive Wigner function. So this is an example, a concrete example of a system which has a positive Wigner function, which satisfies WKB, but nevertheless still contains non-classical properties in the sense that you can exhibit situations where the Bell inequality is violated. So this is a concrete example, by the way, which shows that the conjecture of John Bell in his chapter 21 is indeed incorrect. So now let me come to the end of the talk. So where do we stand? So we have shown that the question of whether the perturbations are quantum or classical is a subtle question. It's not obvious at all, but we have shown that the usual claim, the standard claim that you can always reproduce the correlation function in terms of stochastic correlation function is indeed true, but nevertheless, it should remain some quantumness in the system if we could find, let's say, the Revsen operator, the operator that keeps this quantumness. And if we could measure this, first of all, define and then measure these operators using the CMB data, this would be a way to find a signature of the origin of the perturbation. So the question facing this situation is that, can we do it in practice? And this is the question that I want to address in the 2 or 3 minutes that remains. And unfortunately, this is here that the bad news are going to come. I believe that the answer to the question I have just asked is no. And why is it so? It's because what I have described would require the measurement of at least 2 pseudo-spin components in the example that I have given. And more generally, you would need the measurement of 2 non-commuting operators. And this means, in terms of cosmology, this means a measurement of curvature perturbation but also another measurement of a quantity which does not commute with curvature perturbation, typically the derivative of curvature perturbation, which is the momentum. But in cosmology, the momentum or the derivative of curvature perturbation is associated to the decaying mode, which is extremely small and which is not possible to measure. And it's, I believe that it is so small that it's not even a question of technology. It's so small that probably we won't never be able to measure it, even maybe in 1,000 years. I mean, the question is to measure something like exponential minus 50. So, yes, so I acknowledge that the situation is a bit frustrating because at the theoretical level, in principle, I think we have now a clear view and a clear understanding of the situation. And indeed, it remains something quantum in the system that in principle we could measure. But in practice, I think this is unfortunately impossible. Another point that I wanted to say is that the Bell inequality that I have discussed before was formulated in Fourier space, and to be really physically relevant, it should be done in real space. But we have shown recently, and this will appear soon on the archives, that in fact the discord survives in real space. So this point is not really an issue. And so the question facing this is, do we have established a theorem, which would be like a quantum censorship or something like that the quantum origin of the perturbation is hidden from us forever, as a singularity in cosmology is argued to be hidden from us by the presence of an horizon. Here I would say not yet. I think there is still a way out. And the way out is the following one, and I will conclude with that, is that clearly, if we want to detect a quantum signature, we can rely on something which requires only the measurement of one component, so curvature perturbation, because curvature perturbation, we measure it very, very clearly and very precisely. We cannot measure the momentum, but curvature perturbation we can measure. So this means that it must be something which depends only on curvature perturbation. And so the idea would be to measure curvature perturbation only, but at different redshifts, so at different times. And this is something which is very well known in quantum mechanics as well. It's called temporal Bell inequalities or Legge-Gark inequalities, which is exactly that, which is trying to assess or to prove the quantumness of a system, measuring a spin at different time. And so we are investigating this question at the moment, but we have already proven that if we use the fictitious spin operators that I have shown before, and if we place the system in a two-mode squeezed state, then Legge-Gark inequalities are indeed violated for that case. So this is our hope. We are working on this question. We hope that this is a way out to the negative result that I have discussed before. So the hunt continues. And let me close very briefly. I just recap what I have said. So according to cosmic inflation, the CMB are placed in a strongly two-mode squeezed state, which is a discordant and entangled state. So very quantum, a state which is very quantum with quotation marks, if you wish. However, a signature of this nature seems to be hidden in our inability to measure the decaying mode. So maybe this means that we will never be able to find a direct proof of the origin of the perturbations. It seems that there is only one way, at least at the moment, I can see only one way out, which would be to measure the perturbation, but at different time. And this naturally leads to the concept of Legge-Gark inequalities that have been studied extensively in the literature outside cosmology. So what we want to do now is to apply the Legge-Gark inequalities to the perturbations. And maybe the last thing I can say is a takeaway message. So inflation is known to be a very successful scenario of the early universe, but I want also to stress that it's a very interesting playground for foundational issues of quantum mechanics. I believe inflation is the only situation, and maybe this is going to change soon. And I know you are involved in this study, but as far as I know, at the moment, inflation is the only situation in physics where you need crucially general relativity and quantum mechanics to describe to derive physical predictions, and where at the same time you have very accurate data. These three things at the same time, I believe so far, inflation is the only situation where this is true. So this is a situation which is very interesting for people interested in quantum mechanics. And I stop here, and thank you very much for your attention.
Thanks. Thank you very much, Jerome. I think it's what you said towards the end is really summarizes the subject. And I think, I believe personally, my belief is that more than inflation, this is even more fundamental, what you are chasing. So I would definitely request you to continue in this direction, in this endeavor. So it's very beautiful talk, very
Thank you.
enlightening. So let me ask our audience if you have question. I could see there was a question and I requested the person to not to ask because there was only 2-3 minutes. So if you could please kindly send, and if you want to ask now, please do so.
Hi, Jerome.
Hi.
Yeah. So my question is regarding this quiz-state formalism.
Yes.
Uh, when initially you have mentioned about the single field, I can understand. But what about if you have many fields? Then how you can implement this methodology?
Yes. So if you have many fields, I think this would change a little bit the formalism, because as you know, in the case of a situation where you have many fields, you have also not only adiabatic perturbations, which are the perturbations that I have discussed, but you also have entropy perturbations. And that at the level of the equations, we know that uh, the two are coupled. So the entropy perturbation sources the adiabatic perturbation. So this is why the adiabatic perturbation in single field inflation are constant on large scales, but in a situation where you have many fields, they can evolve with time, simply because now there is a source of which is added and which comes from the entropy perturbations. So in a quantum mechanical language, I think this situation you would have squeezing, but at the same time you would have like a force oscillator, in fact, like a force on the right hand side of the equation. So probably this would modify the evolution of the quantum state in that case. I believe, by the way, that this is a very interesting question, because to my knowledge nobody has worked out the details of this, but I believe this is what would happen. You would add a
Working on this problem for long, and I actually trying to see that how it goes. But yeah, I feel that it also depends on what kind of interactions you are considering between the multi fields.
I think what I have just said is completely general. No, I mean, whatever the interaction that you consider, of course, working at linear level of perturbations, you will always have this entropy perturbation that would source the evolution on large scales of the adiabatic mode, no, whatever the form of the interaction.
Okay, thank you.
You're welcome.
So do we have other questions from the audience?
So I have many questions, but I also see here some people in the audience from, who have worked a lot on these two-mode squeezing. So I see Animesh, for example. I don't know whether they have questions, but maybe I'll start.
Please,
So
yeah.
one of the things is that, you know, even before the Revzen paper, but maybe Revzen cited that, is, do you know there's this work by Vutkaevich and Banaszek?
Yes, yes, yes,
Yeah.
yes.
So this number parity, photon number parity, which
Yes.
can also measure.
Actually, those people have precisely done what I have described. So these people are among the first to have defined concretely these pseudo spin operators I was discussing maybe too quickly.
So that will not make the task easier, I guess. It's the same kind of operator as you have considered, right? The other thing is, generally in quantum information, if x1 minus x2 and p1 plus p2 is less than 1, pre-normalized, we are happy to call it intact. I mean, there are also these separability criteria by Simon and others, which says that as soon as you get below the x1 plus x2 uncertainty and p1 minus p2 uncertainty, as long as the product is less than 1 in appropriate units, it is entangled. So even without measuring spin operators, you still have to measure momentum differences and position sums of the two modes. It is, even though Wigner function is fully positive, you are rightful to call it quantum if x1 minus x2 and p1 plus p2 uncertainties are below a certain number. You see. But you still probably have to measure the momentum modes.
Yeah. This is what I was about to answer, to say, sorry. Yeah.
Right. And in case of these momentum modes, I wonder, so what you're doing is kind of a trick people use in harmonic oscillators, right? So you evolve in certain times, so position becomes momentum, right? So you will measure position at a later time, which in the Leggett-Garg kind of thing, what you're telling. But the rate of evolution is very much dependent on your frequencies, right? So for a kind of a position variable to go to a momentum variable, it takes all the time of like a period's time, in whatever is a relevant frequency. So do you know like what kind of time eras over which you have to measure the redshift correlations to conclude something about?
So if I remember correctly, I think I mean difference. In terms of redshift, a difference of a few was sufficient to obtain a violation. But in redshift, of course, because in time this may mean a very large time.
Okay. I see. So maybe some extrapolated data would be there from a previous. You can kind of extrapolate the data to the past or something.
Yeah. So to do this measurement, I think you need you need something which is quite fashionable at the moment, meaning you need tomography of the power spectrum. So because you need to measure the power spectrum at different slices in time.
Right.
People are hoping to do that soon, for instance, with Euclid and things like that. So.
I see. That's interesting. Yeah. And one last question I had is that somehow, so this goes back to these CKs, which you say are kind of combined perturbations of the scalar field and the gravity, right?
Yes.
And now I don't know how people are measuring CMB. I can understand that you can separate out the K modes, the K and minus K modes from some Fourier transform, I guess. But can you separate out scalar field perturbation and gravitational perturbation?
Yes. At first order in the perturbation, the three types of perturbation evolve independently. So there is no problem. Of course, if you go to higher order, this will no longer be the case. But at the linear level, this is the case. They evolve independently. So actually, exactly the same discussion could be done for gravitational waves. I mean, primordial gravitational waves, of course, not the gravitational waves that have been detected.
Right. I see. I see. And then there, what you are kind of the quantum fluctuations you are seeing of the gravity part is the one which is modified by the scalar field's classical potential, right? Is that that's kind of what you are pair creation in the gravitational sector due to the scalar field, is that kind of reversing the situation?
No, I would say that the pair creation in the gravitation, so you mean gravitational waves, tensor part,
Mm-hmm.
yeah, I would say they are independent of the scalar sector precisely. So they,
Okay,
in some sense, they are universal. They do not depend.
right.
What depends on the model of inflation, on the potential, is the relative contribution of the tensor and the scalar.
I see. Okay.
In fact, if you calculate the power spectrum of the gravitational wave, it depends only on h, the Hubble parameter during inflation.
I see.
While for the scalar perturbation, it depends on h, but it also depends on the shape of the potential.
Hmm. So I guess what you were saying in the end has more chance with the gravitational waves, because maybe the time evolution is the frequency of that wave, and
Yeah, but there is a
not that.
decaying mode as well for gravitational waves, and so I don't believe that we will be able to see the decaying mode. We have not even seen the growing mode of the
Okay.
primordial gravitational waves.
I see. I see. Okay. Okay. Thank you.
You're welcome.
Mhm.
So I have some questions. So or maybe Santan has a question. Please, Santan, go ahead.
Jerome, I have one more question regarding uh, like the system we are considering for this kind of setup. It's like completely a closed quantum mechanical system. If there is a quantum dissipation, or if you have some kind of open quantum systems, then how you proceed with this kind of setup?
Yes, so this is a calculation that we have also, I did not have time to discuss it, but we have done this calculation. So if you assume that the perturbations are an open quantum system interact with some environment, with some interaction that you can postulate in order to achieve decoherence, well, in that case, of course, and it's not a surprise, you find that the amount by which you violate the Bell inequality is reduced. And this amount depends on the strength of the interaction between the perturbation and the environment, and that a priori we don't know very well, but it's true that if the interaction between the environment and the perturbation is very strong, you can even destroy the violation of the Bell inequality. So it's really model dependent, but
Okay.
yes, it's an important point. Thank you. And the same danger, the same threat would be present, of course, for Legge-Edgark as well.
Thank you, Jerome.
You're welcome.
So in some sense, what you are saying is that it's becoming even harder, because we know that inflaton also has coupling to other degrees of freedom to
Yes.
heat the universe.
Yes.
So essentially, they will all get entangled with other degrees of freedom. And
exactly.
So it become even harder to extract the data, even if I see the,
exactly.
It's a wonderful clarification. The clarification which you have made here in these sequel of papers is amazing. So
thank you.
very nice, very nice.
Thank you.
So even in tomography, it would be, even if you do tomography, it would be extremely hard.
Yes, well, it's model dependent. So, I mean, I don't know exactly the strength of the interaction between, well, I don't even know the nature of the environment for the perturbations. There are many models. So which one is the dominant one? What is the interaction, the strength of the interaction? It depends on all these questions, but it's clear that all that which is necessarily present does not play in our favor. That's clear.
No, that is very clear, very evident.
Yeah, unfortunately, yes.
Yeah, Sayantan, if you have a question.
Yeah, so my question is, like in CMB experiments, what people exactly measured to probe this kind of violation?
Uh, Violation of the Bell inequality, you mean?
Yes, yes, yes.
Ah, they don't do it.
Oh,
They have never tried to measure. Well, as I have explained, they would need to measure the decaying mode. So nobody has ever measured the decaying mode, and nobody will.
okay.
I think, yes.
So any other question? If not,
Maybe,
yeah, please.
okay.
No, Sogato,
Yeah.
please.
No, no, I also just quickly wanted to introduce Jerome to, so our third organizer is here, I see, Vimshik. So maybe he was a bit late in coming, but yeah, Vimshik is around.
Oh, yeah.
Um,
Jerome, thank you very much for your talk.
it's
Okay,
nice
thank
to-
you. Thank you very much.
Thank you for your attention. It was a great pleasure for me.
No, yeah, it is wonderful that you spoke and you clarified some of the many of our doubts, so which is very nice. Many of our colleagues are coming from quantum optics, so it's you found your own home.
I feel at home.
At home, definitely. So
So,
maybe we
Jerome, maybe-
close the talk.
Yeah.
You know, I stop recording and then we can discuss privately.
Yeah, sure.